Alrighty. Well, happy Thursday. We're going to continue on with linked lists. And we got a little bit behind, but it's okay. We'll get caught up here. It's not too big of a deal. Um, Doing trees and priority queues should be okay. If we need a little more time, we can bump into the next week because again, we don't go super deep on these things here. We're just kind of introing these later topics as we go. Should be a lot of fun. So today, right? I need to give you last semester's or last year's midterm so that you can look at it before Tuesday when we do midterm review. Okay. Ideally, you've looked at it, tried it, those sorts of things. Midterm review should be relatively short. I just need to go over the answers. It's the only plan I have for new stuff. So we will have a lab on linked lists. So after lab, we can come over and do the midterm review. Uh, It'll be pretty quick. And then Thursday, the 27th, the midterm will open. I have no plans to watch you take a test unless you would like me to sit here and watch you take it. Happy to do it if you want. It's just terribly dull. So it'll open on the 27th. It's not timed. It's open book, open notes, open internet, but not open neighbor. You don't get to work together. This is your individual effort. This is really just a checkpoint. Just check in, see how things are going. Uh, Before you do the midterm, you'll want to have done the quizzes. Sorry, I got those in late here. So at least look at them. If you don't turn them all in, that's okay. I didn't put due dates on them here. I should have had them all along and I just forgot to import them. Sorry. So there's a bunch of quizzes out there from the first 7 chapters, but not chapter 3. Essentially, quiz style questions. Questions like that will be on the quiz. Right? Just real short, 1 sentence. It's not a paragraph. Just give me like 1 sentence here for this, for a lot of those. And then 3 long answer coding style questions. So here, I can just go grab that right now, I think. Let me go to last year, 2024. And that was like a year ago, wasn't it? Quizzes, midterm, preview. Yeah, this time limit I'm getting rid of. It's not applicable here. So let me go. Can I just print this to PDF, right? Okay, let's go print to a PDF. So it's going to be long just because every question is like a long answer box and essay box. It just looks really long. I promise it's not that bad here. Okay, so let me go ahead and print. Go to PDF. Here's CS 2001 practice midterm. Excuse me. All right, we'll go back to our course and I'll upload that for you here. Let's put in files. Upload practice midterm. Okay. So just real quick, I write the questions myself, so there's probably typos. If you're not sure about it, ask me. Right? I'm not going to tell you to go away. Um, so again, starting with the academic integrity policy, you get a free point for saying, yes, I will not work with another person. Someone actually researched this, and I thought it was interesting that if you put this at the end, people are more likely to have cheated and then just say, oh, sure, I didn't cheat. But if you put it at the beginning, they're less likely to cheat because ahead of time they've agreed to not cheat. Versus, oh, I got through a bunch of questions, I cheated my way through, and now you're asking me if I cheated or not. You're like, oh, of course I didn't cheat. But if you ask them up ahead of time, they're less likely to cheat. Another fun survey, because we love bashing on other institutions of higher education because sports ball. When they did a research study, they had people in specific clothing of a given university, similar to some students here, and they had people in the opposing team's outfits. So probably Ohio. I don't know if it was Ohio State, whatever it was. Someone wearing Ohio State after 2 minutes in an exam got up, handed it in, and it was a like self-score your exam sort of thing. You're turning like, I got them all right. And if the opposing team cheats, you are less likely to cheat because they're dirty and we're better than they are. If someone on your same team cheats, you're like, oh, someone else is doing it, I can do it too. So there's this like weird group think that happens. But imagine someone from Ohio State is cheating on the exam here, and you're better than that. Okay, just keep that picture in your head. Ohio State's dirty and they cheat. We're not going to do it. We're better than they are. Because what's the point of having a brand that says we're better than everybody if you don't pretend like you're better than everybody? Right. Okay. Then some quick true false questions in here. Some short answer ones. Again, pretty quick. Like in English, tell me what this does. Here, how would you do this with the linked list? Again, we'll go through some of these things here. So it's about 15 questions that are like quiz style questions here. relatively short here, then 3 long answer questions here. So this one is based on two-dimensional lists here, lists of lists. So you'll get a different question on two-dimensional lists that has something silly you have to do with a 2D list here. Right, so in this one here, it's the sum of prime values or values in prime indexes given some 2D list as an argument here. Returns the sum of all prime number values and values whose index is prime here. So, right, imagining index 0, 1, 2, 3, 4, on and on and on and on as we go. So you have to look at the index value and you have to look at the value itself. Just iterating through lists, having some practice there. Um, and then make sure you don't add them twice, right? That's another thing here. And then a question on recursive functions. So again, something about recursive functions. It won't be this jumble function here. So this one is a private helper function. My little hint here, private helper functions are nice to help us track additional things that you can have. Here's the public function that's easy, and then the private function has additional variables that we have to track, like with the Fibonacci. The better recursive version passed in what we're currently doing so we can add up. We know it's not as efficient as a loop, but again, it's faster than adding up one, a bunch of million times here. And then the second part of this question is do it iteratively. That's a weird like pop-up in the way here, but iterative. So do it with recursion and do it with iteration without recursion, right? So this will be something you could do with a loop. You'll do recursively for the exercise, and then you'll just do it with a loop here. And then the last question is, given some sort of UML, write some class here, and then write your unit test for it. Again, not super long here. This is a relatively quick exercise. So we write I don't know what this pop-up is, but that's okay. So making sure that we get 100% code coverage means that if there's an if-else block, I'm going into the if with a test and I'm going into the else with a test, and I'm testing both cases, right? So that means more than one test if it's going to be an if-else block there. You get 100% code coverage, right? So here's a quick little class. Again, with UML, it's you get the class name, you get the attributes, and a colon, the suggested type. Python is just a suggestion here. And then you get the functions there. Right, so class name, attributes, functions is just a quick, nice little way of putting a picture for a class. I think we looked at this in the Zybook a while back with the pictures they had with UML. I don't know if we've done too much with it this semester. I think we're supposed to. I got to look at the list of course objectives again. It's just a quick picture. So again, basically the description here with what it should return, right? So this returns the base, whatever cost here, sets. And that was it. So like 3 questions, right? Long answer style questions. So 2D lists, recursion, iteration, and then write a class with tests. Those are the 3 long answer questions. And again, you got as much time as you want on it, essentially, right? Because we're, over the weekend, sure. Or no, wait, this was over break, right? Because we've got the extra time because this goes over break here. If you'd like to get it done before break, fantastic. If you want to wait till after break, fantastic. If you want to spend your break working on it, go for it. Right, as long as you get it in by 3:11, I'm happy. So 3:11, 2 p.m., I'll go over the answers. I'll show you a quick solution to them. Again, timing-wise, ideally, they take me about 5 minutes each for the long answer questions. I'm assuming it takes you guys triple that and then doubled again, just in case. So I figure each one of those is maybe 15 minutes to an hour, or 15 minutes to half an hour for you folks to do. And then if you had enough time, we could do it in a class sitting, right? If that was 15 minutes each, a minute per short answer question gets you done in about an hour and 15 if I like to watch people take tests, which I don't. So, and again, it's not useful if you can memorize crap. There are time constraints in the industry. You don't have unlimited time to work on projects, but rarely is it you have 1 hour to get this done, do it now while someone watches you. Rarely. That's generally accepted will not get good results here. So don't expect that same thing for you folks. All right, so that's the practice. So on 225, I'll go over the answers to that. We'll look through it real quick. Do take a look at the quizzes. I think a couple of people have turned them in. Thank you. Again, sorry to dump them all on you late here. At least look at them so you know what the questions look like. You don't have to answer them right away if you don't want to. They should take, maybe 10 minutes per quiz. So, it's like an hour here. Not too bad, I'm hoping. Again, sorry, I got them in late, but look at them, right? And if it makes no sense at all, please come and ask me. Right? Like we've got some disconnect here if the questions don't make any sense to you. If you're like, oh yeah, I can answer that if I spent a few minutes, great. Then you're in good shape. Okay. Eventually you do have to do them. Right? I'm giving you points for the quizzes, and that's part of your final grade here. But you don't have to get them done before the midterm if you don't want to. All right, cool. So now we're going to move on to linked lists. Let me fire up PyCharm here. So we did our singly linked list that each node knew what node came after it, right? So this node knew what came next, and this node knew what came next, and this node knew what came next. So we could get pretty good performance, right? Constant time performance for taking away from the front, adding to the back. So as a queue, we were super fast, right? Super fast because we can take away from the front, add to the back, constant, no matter how many end items we had. This is an improvement over our array-based lists, which on average were constant, but eventually, every so often we had that doubling. So our worst case performance was O of n, where we did have to do the doubling, copy this many things over here. So we always, even in worst case, are O of 1, constant time speed for these things here. So really fast, really nice. We like that. Now, it works as a queue, but not as a stack, right? Because we can't put things onto the end and take them off the end, because getting to the end means I have to go start at the first node and go to the next node and go to the next node and go to the next. For every n items, I have to walk those n items to find where the last thing is, right? If the only thing I know is where the front is and where the back is, but just knowing the back doesn't mean I can take the back off, because then I've lost where the back is. If I remove that back item, and I need to put self back to something here, but I can't get to the new back node without starting the front and going all the way here. So now we're going to introduce the doubly linked list so we can solve that problem. If nodes know what comes before and what comes after, we can do that. We can take something off the back here and then just back it up one because we know what comes before it here. So we're going to make a new class here for our doubly linked list. Doubly linked lists. That should probably be singular here, not lists. Let me rename that. That's going to bother me. Nope. Rename. Refactor rename. Just list here. Okay. So our class for doubly linked list. And we're going to define a private class right inside of here then is a node. And then we're going to define our node has some data that it looks at. It has the front and it has the back. Was that what we used? We said front and back. Oh, we had next. So let's go. Next is none until you tell me otherwise. And I'll have a previous is a none until you tell me otherwise. Okay. So if you tell me what comes after you, what comes next, I'll know it. Otherwise, you don't have a next. And if you tell me what comes before you, I'll know it. Otherwise, you don't have one. Right. So then our node then just says self.data is the data, self.next is the next, and self.previous is the previous. Again, these aren't private or anything. It's just a way for us to hold those pieces of information. It's an implementation detail. No one ever touches nodes directly, right? They're not going to use them directly here. They're just going to use my doubly linked list and know that whatever public functions I give them, like append front or add back, remove front, remove back, those are public methods. We can build this into a nice deck here, which can function as a queue or a stack. If you're a deck, right, you get both with that one here. Just by using those details. Right? Okay, so then when we define our init for this one here, we have a self.front is none, and a self.back. Oh, I'm sorry, these should be private here. Front and back is none. So I don't know what they are until I know otherwise. A self.number of items is 0, right? We can copy a lot of this out of here, right? So we've got length, we've got is empty. We'll steal those ones here. Then append, a lot of these are pretty much the same here. So let's go grab all these here and throw them in. Few things become different though. Right? Hopefully this isn't too bad to go about it. Oh, this route here. Why is it all tabbed in so far? There we go. Bring all that back one tab. So to append a piece of data here, we're still checking, hey, if I don't have a front, I'm empty, right? My front is the front, my back is the back here. I still have nothing in front of me. I still have nothing behind me. Easy. Right? So this is, and maybe we want to call this one add back here, just to be, I think that's consistent with our deck. We had add front, add back, remove back. Okay. Otherwise, then I'm going to make a new back here. And if I have a new back item, then I need to set a couple things. So what comes before this one here then is self.back, right? I have a new back, so to be able to link backwards here, the new node knows what comes before it is what used to be the back, right? Then the current Back then, right, needs to know. Oh, I'm sorry, we're already setting its next here. So this is the backs. Oh my goodness. Yeah, next and previous. Yeah. So backs next, we're setting to this one here. So we're adding the link in. This is what comes after it. And the one that we're adding says this is what comes before you. So both link to each other. That's the doubly linked, right? They're linked forwards and backwards here, right? And then we change where the back is, right? It's no longer the back node. It's the thing that comes after the back node here. So that works the same. So to remove from the front, and we check, hey, we're empty, nothing happens. Otherwise, then we're going to go move the front item here. Now, the only piece you need to change for this one says, hey, the new self front, then previous is none. Because what was next here, right? So we had front, and then we have the next one here. What was next knew that the front was previous, right? So if we draw this as a picture, sometimes this is, I should have brought my tablet. I said that last time and I forgot again. All right, so if we have our node here, right, we'll say this one's the front here. So it has some piece of data. It has no previous here because it's the front node here. It has a next, which is another node here. Oh, goodness. Why does Word lock up? This is Word. It should not be that hard here, my drawing tool. Come on. My whole laptop. There it goes. Wow. Wow, that's fun. Drawing tool. Yes. Can I change? There we go. Right, so this one here, it has some piece of data. I don't know. We'll just put like the number 1 here. We'll put the number 2 here. So this one's next points to this one here, points to 2. This one's previous points to this one here. We have a value. It has no next. There's nothing here. So we want to remove the front. We're going to take this one off and say, okay, front now points to this one's next. Well, that's over here, right? Follow that chain. And then we say, okay, hey, new front, this one's gone here. Don't point there anymore because we want to get rid of that one, right? So make yours none because you're the front. There should be nothing before you, right? Because if you hold on to that link here, then we can traverse it and we'll have that reference about the garbage collected. Weird stuff will happen, right? We rely on the front node having nothing previous to know that it's the front node, right? Okay, so removing from the front, easy. We just have to go set that one, right? I'm sorry, adding to, goodness, where were we here? Removing from the front, right? Setting it to none. And then, hey, if front is none, uh-oh. Well, if front is none, we can't set previous, right? So this really needs to be if it's not none, then we can set a previous to none. Otherwise, we're going to get one of those null reference exceptions and we're going to crash because you tried to set something on a none, it doesn't exist, right? So only if front is not none, then can we change previous. Because if we went to none, if the thing that came after me, if I didn't have anything, if I was a list of one thing, right, front moves to front's next, which is none, cool, we're none. Then we take away our number of items. So find is the same, get item is the same, set item is the same. Those all work the same here. So now we want to add front, right? So we can also add a add front, which will be an O of 1 operation here. So we're going to define add front given the data. Let's see, this is add back, right? Sets back here. So again, we want to check if front is none, right? Then we just do this. Great, we got a new node because we were empty. If we weren't, then, right? Now instead of changing the back here, we're going to change the front. So instead of saying my back next, here we're going to say my front's previous. Hey, the thing that comes before my front node here is now a new node. And hey, the thing that comes after the new front is self front, the old front, right? Put something that comes before the first node. Hey, so this is the first node. I'm going to put something that comes before it. Let's make a new node here with 5 here. The front node's previous now points to here. It's not none anymore. And hey, this new node, your next is what used to be front here. And then, hey, front, you don't point here anymore. You point at this new node. Now we've added something to the front of our doubly linked list. So we can use those links, front and back, to go add stuff in. So front's previous, and add a new previous. It was none. Now it's a node. And what comes after that new node is the current front. And now we're not changing back anymore. We're going to change front to front previous, right? So we're just adding it in. So we can add to the front, we can add to the back, we can remove from the front, we can remove from the back the same way here. So this is, my goodness, why is the padding all wrong every time? Remove back. So to remove the last item here, this is my back data. And now my back will move to the back's previous, right? The thing that came before the last item here. So actually we should have been tracking back at the same time here, right? So this one's the back. Thing that comes before you is the new back, right? And then new back, you don't have a next anymore, right? Break this link here, break that chain. So once I set that, then I can say if it's not none, so if self back is not none, self front is none, and then if back previous back's next is now none, right? Because we need to make sure we take out that link here once we remove that back item here. So to remove the back, the new back goes here, and then it's next. Sorry, it's next is none. Break that link. You don't point to anything. We've removed it here. So someone had asked me if we should test our code, and yes, we definitely want to test it, make sure this stuff works here, because I probably screwed something up somewhere. Very, very easy to have happen. So we just rename this one here real quick. Rename singly linked list. Got a doubly linked list here, and then I'll go add a main Python file here. And we'll go try them out here, because we didn't do that before. So we're going to say from singly linked list, import singly linked list, from doubly linked list, import doubly linked list. Let's try it. I don't know. So for number in range 10, let's take we need a singly linked list, single list. I don't know. We don't want to use the same name as the module here. Is a singly linked list. Cool. And then we'll take our single linked list, and we should be able to append the number here. And then while my singly linked list dot single linked list, goodness, come on, single linked listed. Oh my goodness, Eric, refactor, rename that. Not listed, just list. There we go. Dot is empty. While we're not is empty, then let's go and print it off. So we'll print the singly linked list dot remove front. We'll take from the front. Right, so we should be able to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If that worked right here for the singly linked list. Did remove not return that value? We probably didn't return the value. Yeah. Oh no, it's supposed to return the data. Shoot. Remove front. There's the data, return the data. I'm running the wrong file. I'm running the singly linked list file. We got to run main here. So let's go run main. There we go. Hey, now we get 0 through 9. Life is good. Okay. Let's try the doubly linked list here. So we're going to take all of this, repeat here with a double linked list. There's a doubly linked list here. And we'll go, and we want to add add back, right? For that first one here. And we're not empty, remove the front here. That should we get the same thing again then, right? 0 through 9 repeated. If we're removing from the front, but if we remove from the back, we should be able to get them in reverse, right? 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Doesn't crash on us. So I feel pretty good that this is working. We didn't try a whole lot of things here, but that's okay. So we've got our singly linked list and our doubly linked lists. And now you might be thinking to yourself, this feels like a lot here to have to check if we're none, if we're not none, setting things to none, not setting things to none, it's obnoxious, right? But we did it. It's just annoying. Could we do it better? Yes, I'm so glad you asked. We could do it better. I've had a lot of coffee today. I had a 7 a.m. meeting for breakfast, and the waitress was amazing. She just kept filling up my cup. And I think after like 6 cups, she almost left the pot for me. But I will just drink coffee nonstop here. And then I got more. This one's my espresso drink, which is good. And they sent me a to-go cup too. It's amazing. Like I thought they only did that in the South. But this sweet lady, she's like, "Here's a cup to go of coffee." It's like, "You're my new favorite person." It's amazing. But it's like $3 for a cup of coffee at a Comey. Like, feels excessive for $3. I don't know. All right. Yes, we can do better. So let's do better. So let's go add a new Python file here. Let's call this a circular doubly linked list here. Now, we're essentially a doubly linked list here, but we're going to be smarter about it here because we can be a circle. And if we're a circle, life is just so much easier here. Okay, so we'll go erase all this nonsense. So the premise with this one here is that I don't want nuns because nuns hurt. Nuns suck because you can't perform an operation on a nun object, on a nun type, and then your program crashes. A null reference exception in other languages here. They're no fun. So if I always have a node, then I never have to check for nuns. So what we're going to do is we're going to have this dummy node here. This is my favorite technical term. This is our dummy node. So we will always have a node here. Its data is none. It doesn't hold anything. But when we start our doubly linked list, its previous is itself, and its next is itself. So we always have something. Okay? If we always have something, then the rule with our dummy node is its next is always the first thing, and its previous is always the last thing. Okay, so our dummy node will always exist. We'll always have a node in memory, so I don't have to worry about nuns. And to find out where things are in my list, I know its next is the first, and its previous is the last. And it will always point that way. So we're going to make this into a circle. So if we're going to add a 3 here as a node to the front, right? I'm going to say, okay, let's add a node. If you're the front, now dummy's next becomes you, right? Because you're the new first. So instead of pointing to itself, it's going to point to you. So, okay, hey, I'm adding to the front here. If you're the front node, your previous is the dummy node. That one's easy, right? My next value should be what used to be dummy node's next. So I guess I shouldn't have erased that yet, which means my next value is the dummy node, because that's what its next was. Right? So we're adding a node and joining it to the link. Hey, my previous next is me, my next previous is me. Right? And I'm going to go in between the dummy node and whatever used to be first. Right? To add to back, same thing here. We're going to say, hey, the previous node of dummy always is the back. So whatever back used to be now I'm the new back. So I'm going to add a new node, right? My previous, right, what comes before me is what used to be previous, what used to be the back, right? In this case, so my previous is the dummy node here, because that's what used to be the back. What comes after me is, no, I'm sorry, what comes after me is the dummy node. Sorry, what comes after me is the dummy node here, right? Because I'm the last here. And what comes before me is, I forgot to update this one here. So that's why this isn't working here. So this previous here, sorry, should have been moved to this one, right? Because what comes after me is here. I'll show you. So then what comes before me then is its previous, right? So now I'm going to point here instead, and I'm going to point here, and then I go change my link. Say what comes before me, I come after you. So no longer after here. Oops, I lost my box here. You point to me, I'm next here. And then what comes before me, right, which is so what comes after me, I come before you. So its previous now points here. Sounds really crazy. I promise it's much easier in code. So our links are still the same. Now we don't have a front and back anymore. We have a self.dummy, dummy node, equals a self.node. Now this one we can't set to itself very easily here. So we're just going to say if data's none, then we'll say self.dummy node. Next is the self.dummy node. And self.dummy node previous is the self.dummy node. Right? Join those links together. So it points to itself. It's a circle, right? Now, when I go add something, I never have a front that's none. Never have any of this here. So all I need to do here then is go and add this node here. So to add to the front, the dummy node's next becomes the new node, right? Because you're the front. You're the immediately after. Dummy's next is always the front. So dummy's next becomes this front node here. Well, the thing that comes before this one here is the dummy node. Because I'm in front, I point to you. What comes after me is what used to be after dummy node's next. Right? So my next then is dummy node's next. Whatever used to be in front now comes after me because I'm the new front. Okay, so we go and add myself in. Now, this is actually a little bit easier to do in multiple steps here. So we'll say, hey, this is the new node here, then equals this one here. So a new node is, before it is the dummy node, after it is whatever used to be after. So we're going to create a new node, then we're going to go fix those links. Hey, what comes before me, I come after you. And what comes after me, I come before you. We have to add ourselves into the chain. So the new node's next previous is the new node. And the new node's previous next is the new node. Right? Thing that comes after me, I come before you. Thing that comes before me, I come after you. And this is always going to work because we have a dummy node. There's always a node. We never have to worry about nones, right? If next was none, you can't set previous of a none, right? That was the issue we had before, right? Didn't work. So this is the code here, which is nice. So now adding to the back is the exact same thing here. Let me just go grab this one here, except we add a different direction. So adding to the back means the thing that comes before me was the dummy node's previous, right? What used to come before the dummy node was the old back, right? And what comes after me is the dummy node, right? Because I'm the new back. The back's next is always the dummy node because the dummy node's previous is always the last thing. And again, the same operation. What comes after me, I come before it. What comes before me, I come after you. We just connect those links here. So now we're circular doubly linked lists here. Now we don't have to worry about if back front is none or front is previous is none or any of this stuff here. We can quickly remove it very easily here. So the data then is going to be off the dummy node. So this works out so much cleaner here for the if else. So it's the front is dummy node's next data, right? Dummy node's next is always the front thing, okay? Because it's always the start. And we already checked to see if we're none or not. So the data's there. Then to remove it, we just need to pull it out of the list, right? So the dummy nodes next here, and this is probably easier to say the node to remove. Again, gets a little cleaner here. It's dummy nodes data here. So we're going to remove that node, and then we've got the data is the node removes data here. So to remove an item, we just take it out of the loop. We say, okay, the thing that comes after you, your previous, is my previous. The thing that comes before me, your next is my next, right? Just jump over me. So if we have a big list of doubly links here, we just jump over. So let me draw just a bunch of doubly links real quick. I can show you the jump. So again, we've got the dummy node here. That's fine. That one's none. And we got a node over here. Let's do like 1. Let's do a node over here. There's 2. We'll do a node over here. It's 3. Okay, so next is always here, right? There's next is this one here. Next is this one here. Next is this one here, right? We always know what comes next. And then previous. Okay, previous is this one here. Previous is this one here. Previous is this one here. Previous is this one here, right? They're all doubly linked. They know what comes before, it knows what comes after. So to remove 2, we say, hey, thing that comes after me, the thing that comes before you is what comes before me, right? Don't point to me anymore. Point to the thing that was before me. Jump over me. So we change this link here, say, hey, you just jump over me. Point to my previous, right? And then, hey, thing that's before me, the thing that comes after you, it's not me anymore. It's whatever comes after me here. So break this one here. You just jump over me. We've pulled it out of the list, right? We said, hey, point to what came before me. Hey, point to what comes after me. Take me out of the list here, right? Then we can remove it. So removing the node says, okay, here's my node to removes next previous, right? The thing that comes after me, what comes before you is what comes before me. And then the node removes previous. Hey, the thing that comes after you, it's not me anymore. It's the node removes next. What comes after me? Okay, we've jumped over ourselves in the list, and we can return our data. That's all we have to do. Because we never have nones, we don't have any nonsense to worry about. I don't have to worry if I was the last item here that all of a sudden my next is now none because there was nothing left. I know at least I have the dummy node. So if we're down to we got rid of 2 here, right? And we want to remove the 3, right? We can remove 3 because we'll say, okay, hey, 3, the thing that comes after you here, its previous is no longer you, have it jump over you. Okay, well, now your previous is my previous. Okay, break your link. Don't point to me anymore. Hey, thing that comes before me, I don't come after you anymore. What comes after me comes after you. Pull it out here. And then 3 is removed. Okay, now if we want to remove 1, sure, we can remove 1. We can remove the last item here. We never have nones. Hey, thing that comes after me, well, that's dummy node. The thing that comes before you isn't me, it's the thing that comes before me. Okay, well, now you points to itself. Hey, thing that comes after me, or no, I'm sorry, thing that comes before me, I'm not next anymore. My next is your next. Well, that's yourself here. So your next is now next here. Puts it back in the starting state here. We've gotten rid of the 1, right? And now it just points to itself again. So regardless of how many nodes we have, it still works every time because we don't have nones. And life is good. We like that. Okay, so we can remove from the front, we can remove from the back. Same idea here, it's just a different node here. So instead of it being the front one here, it's the dummy node's previous, right? Because the back is always previous to the dummy node here. Same operation here. Okay, so we could, because we have the same code twice and feel bad about ourselves, turn this into a function. This is remove a node, right? And this is add a node. We could turn those into functions. Wouldn't that be nice? Yeah, that is nice, right? We should do that. So let's turn this into a function here. So I'm just gonna copy it for right now here. So we're gonna define a private function for add node that takes the data, the next, and the previous, right? Those can't be none here, right? Because I need to know, and I will always have them here. Sorry, previous is the previous, and next is the next. That was a bad copy paste. We should probably do them in what order is node in? Node's next and then previous. Yeah, next and then previous. I should do it that way then, right? Next and previous. I was doing the keyword arguments here, but we can do it positional as well if we wanted. Keywords are a little bit cleaner here, but I'm going to do positionally as well. So we can add a node here. So to add a node, right? All we need to do is call self.addNode, given the data. If we're adding to the front, what comes next? Well, that's self.dummyNodes next. What comes before it? Well, that's just the self.dummyNode, right? Add myself in between what used to be the front and dummy node, because I'm the new front, right? You come before me, this comes after me. And we can even be clean about that and say, hey, this is the next and this is the previous here, because that's nice and clean here, right? We don't have to specify, but I think it helps point out what is what here. So adding to the back, again, same thing here. It's the add node helper function now. The only thing that's different now is what comes next now. So if I'm the last thing, dummy node comes after me. What comes before me then is what used to be the previous here, right? Put myself in, right? And same idea with removing here. Let's remove here. So we're going to, now this one is a little bit uglier, but that's okay. So this is a private remove node, then given the previous, given the node, which all we need is the node for this one here. And you tell me what node we're removing, I can go remove it here, right? So the node to remove here is this one. I'll take the nodes. I have the node to remove, right? So that's the node's data. And then the node's next is the node's previous. I'm sorry, the node's next previous is the node's previous, and the node's previous next is the node's next here. And then we're going to return the data, right? So you can say, okay, we can actually just remove this one here and then return self.remove node given, so remove the front is self.dummy nodes next, right? Because next is always the first thing if we're removing the front here. So all of this code here for remove back, we can just get rid of here, which is fantastic. I'm sorry, we're still going to do our check if we're empty or not here. Probably should turn that into a function too because I'm feeling bad about it here, but that's okay. We can return, now it's not my next, it's the previous. Dummy node previous is the back, right? Should we turn this into a check for empty? I don't know. Do we use that more than once? I don't think we use it more than once. Remove node. What does it not like about that? Maybe static. I guess we don't use self. That's interesting here. Wow, really? You need to know which one we're removing. But once we know, okay, sure, that's fun. All right. Now, when we're circular, though, finding a node is different. We don't start with the front here. We start with the dummy nodes next, right? Now, the problem is it's never not none. I'm sorry, it never is none because we always have a node. So what we're doing is while the current node does not equal self.dummy node, right? Once I've gotten to the dummy node, I've completed the circle, right? If I'm empty, I'm already at the dummy node and I'm done. The loop never runs here. Okay. Keep on going, node, 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 node. Walks are the same. Eventually we get back to the dummy node because we completed the full circle here. Sure, works out the same. So the current node then is the same idea here. Self.dummy nodes next here. Keep on going, keep on going, keep on going. We already checked to see if we're a valid index or not here. Right? Next is always the front thing. That's index 0 is always the first thing. You just keep on walking. That one's the same. Same idea with this one. Now that's the dummy nodes next. Right? That's always the front thing. Now, you might be thinking to yourself, now that I can go forwards and backwards, I can improve these algorithms. I'm glad you thought of that because improving a constant in O of n algorithm is good. Now, the problem is we can improve it by at most 50%. And we throw away constants. So, yeah, we made it faster, but does it really matter? No. Sure, it does matter, but in the big scheme of things, it's still an O of n operation. And we can do that by saying, hey, if my index is closer to the back, don't start at the front and count that direction. Start at the back and count this way, right? We can optimize it here to be a little bit faster, right? So I will leave that as a to-do. If index is closer to the number of items, start at the back node, and count backwards, or walk backwards, right? Here, right? That's our little optimization. So we can speed it up. So if you're at the end here, hey, you want item 100 and I've got 100 items, well, now we can do it a bunch faster because I just count backwards here. But again, when we average all this out here, now we're at like half of n here, and half of n is still O of n. We get to throw away our constants because math is fun like that. How you feeling so far? This gets a little nuts, so drawing pictures is helpful. And again, we're not going to write these by hand in the real world because they're already done. Right? We looked at some of these things being doubly linked lists already built in Python, right? When we looked at the standard library, I said, hey, this thing already is a linked list versus an array list. Right? Did we look at that? I thought we looked at that. Hang on. So let me see. Python linked list here. Linked list library. I don't know. Linked list library. With our search here. Linked list preferred. Predefined library. Says the deck is doubly, but that got voted down. Huh. Really thought we had one here. Linked lists. Really? Deck class, double-ended queue is implemented. Okay, this one says it is. No, thank you. I don't want to subscribe. I just want my answers here. So I think we get one here. I feel like we had one. Not have a built-in standard library. There's Geeks for Geeks. Is this it? Making node. Look at that. Look, they have pretty pictures. Their pictures are prettier than mine. I feel bad. I should have asked ChatGPT for pictures. Did I tell you about the one database schema someone turned in to me? Oh, I really have to show you. It's terrible because when you ask large language models to generate pictures, it tries. So it got the word right in the center, and then everything else was literally nonsense garbage. And they turned this in for their final project. Like, here's my schema. Like, oh my goodness. I really hope my 17-year-old knows better than this. Now I have to go ask him. Yeah, I thought there was. Is the deck Python deck implementation? There's a doubly linked list. This one says it is. Okay, in Python. Look at that. So yes, the deck is a doubly linked list because you get that really good fast performance, even at worst case, it's still constant time. So using the deck behind the scenes is doubly linked. So we're never going to build it ourselves. We're just going to use this in the library. But building it out ideally helps you understand why it's fast. And that's really the whole goal. So what we're learning is we're expanding our toolkit to say, hey, here's some cool data structures that are fast at some things and slow at other things. So if I want to write a program that solves it efficiently, which we haven't really cared about up until now, right? The whole previous goal was just get the job done. I don't care if it's fast or slow because we're not doing anything a million times. But as we have to optimize and make things faster because we're going to try and scale applications here, and it's eventually going to matter, yeah, I want to use the data structure that performs most efficiently here. And that's more of the science side of things when we get to software engineering and data science, right? The very technical side of how do I make this thing fast because I have to do it a bazillion times. And every like fractional update is useful here. Um, but yeah, so collections deck. Look at that. Love it. Very exciting. All right. So that's our doubly linked list here. Okay. There's one more layer of this, but I think going into it today is not going to be worth it. Is that okay to push off? Can we talk about it Tuesday? We'll do midterm review and the last little bit of linked list fun. Is that okay? Okay, so we'll have time. The midterm review is only going to take 15 minutes, if that. So we'll have the other hour for this here. So just because I know you're curious and you haven't read the book yet, they're positional linked lists, and we'll deal with positions. And positions gives you a public concept of how to interact with the linked list. Because if I know what position I'm at, hey, I'm currently at this node right here. If I have that as a position, you can add before and after it in constant time. So we expose a position concept so that they can have constant time adds to wherever they are. So if you're navigating around a list of 1,000 things and you remember, hey, here's my position over here, here's my position over here, here's my position over here, any of those positions have constant time adds. So it gives us even better performance, again, at the trade-off of now I have more memory, right? I'm storing a bunch more things. I have to store the position that it's at and remember that here. Now you can get instant adds at any given position here. But to move positions, you still have to walk those nodes. You have to say, okay, what comes next? What comes next? What comes next? What comes next? But we've got a lot of cool trade-offs. We can do a lot of fun things here and make this really fast with positions. So we'll write that code on Tuesday. Uh, Actually, we might be able to get it started in the lab. Are we going to have a lab? I think a lab on linked lists is no fun. Um, yeah, because writing, if we haven't written it yet, we can't do the lab on it. So should we plan for no lab on Tuesday? Because having you write these things that I just wrote is terribly dull, and you can just copy paste, right? I mean, look at the textbook. The author of the textbook does this differently because he loves his inheritance, and it drives me crazy because I feel like that just makes it more confusing. Ideally, inheritance makes things less confusing, but the way he does it just irritates me. Um, but hopefully, seeing it my way and seeing it his way, one of the two will connect with you, and you'll be like, oh, okay, you have that light bulb moment for linked lists. Um, so yeah, give it a read. Let's plan not to do lab on Tuesday then, because there's nothing to do yet. We'll write the positional stuff, so then we can do if we do positionally linked lists on Tuesday, we can have a lab following midterm. How about that? That sound okay? So we'll do. Come on, come on. I should be able to wait 5 seconds without getting irritated, but like 5 seconds just feels like a long time here. So plan for no lab on the 25th. We'll plan for lab on the 11th, right? And we can do our linked list lab on the 11th. Now, once we've done positional linked lists here. So there'll be a bit of a gap, but again, it's okay. You'll use the positional linked list to practice stuff, but writing it yourself is terribly dull, right? I'm gonna write it for you Tuesday and show you how it all works here, and then we're gonna go and use it to do things quickly and see, hey, I can use a positional linked list if this is my goal and this is how I'm going to interact with my data here to get constant adds, constant adds, constant adds, or removes, right? And you could remove a node from a given position like that because you just jump over, right? Super fast all the time. So we'll play with positions on the 11th. So let me add that as an announcement here. So no lab on the 25th. We'll have a lab on the 11th. No lab 225. Yes, lab 311. Is that Enough information? Okay. Can't be blank. What can't be blank? Yeah, my description, but come on, that's a terrible error message. Do better. When you guys write software, do better. Okay. Um, no lab. Yes lab. Yes lab seems silly, but that's okay. I think it's funny. That'll be a good email, right? And you're not, I should have had this like post on the 25th or something, right? I don't know when you guys look at your calendars to remember if you should drive to campus or not. Okay. Anything else? Questions, thoughts, concerns? We've got our project we're working on, right? We did that one already. Our next stacks and queues project. Again, the input and output is rather particular, but this is a very specific format of kind of question based in competitive programming where they get this sort of nonsense. They're like, here's 5 lines of input, go. And it will always look like this. And then it can just check your output here. It's actually really cool. They do some fun stuff here. Like, and you submit your stuff to a website and it automatically tests it and does cool things to tell you if you passed or failed or if you timed out or too slow. That sort of thing. Was it ICP3 programming? I forget what it was called. It has a name. ICPC. There we go. Um, World final. Yeah, this is like a big thing here. But they've got regional instruction, like competitions. North America is in May here. Registration is closed already. Bummer. Our ACM group or the honor society, I forget, some Greek group that's like an honor society used to send a team, and then COVID happened, and then like nobody did anything, and then nobody remembered that was a thing. And I don't get paid to do it, so I'll be honest, I wasn't really excited to go round up students to go do it. And it's not even my class, really. Like the 350 class and beyond is what gets into this here. But they needed a coach 1 year, so I went, which was fun. Um, Efficient champion. So where's their like practice problems here? They've got CPC world final problems. Here we go. Here's the problem set, and here's the scoreboard. So it says, hey, it took 3 tries, but they finally got this question right. 26, 1 try to get this question right. You get, is that points for it or something? I forget how this all works here. They failed this. So you get a bunch of questions you got to go do here. Let's see. Oh, look, Harvard sent a team. There's a really good team out of Canada that had a pretty good. Is there anything Michigan in here? Hey, Michigan Ann Arbor. They tied for fourth out of at position 94 was a high. Oh no, no, 4 points out of 9. Okay, so they were 4 points out of 9 here. 94th position. Got a couple questions right. Let me see here the questions. We go to the problem set, right? This is not all that interesting, but if you're into this sort of stuff, it's fun here. So like, hey, here's n things, one over n, and here's your sample inputs here. So your inputs look like this. Here's integers. Here's integers. Here's okay. Here's your specific. So here's your sample input. Here's your sample output. Here's your input. Here's your output. Right? So that sort of input and output is reminiscent of these kind of questions here. Um, that's all. That's why it looks like that. I'm generally not a fan of those, but doing it every now and then is good. It's good exercise. Um, okay. Questions, thoughts, concerns? Have a good Thursday. See you next week. No lab. We'll do positionally linked lists and midterm review. And then I won't see you the following Thursday unless you want me to watch you take a test. I'll be here anyway because I have a morning class. I think. I don't think they're doing the midterm. I should look at that. I don't think I scheduled them all on the same day because I'm dumb. All right. Thanks, everybody. I'm going to go drink some more coffee.